Hello. The vast majority of Lecture 16b is about vector spaces and linear transformations. And if that's what you're here for, I'll put a time that you can find that content started. However, I hope you stick with me at the beginning. I'm going to do something kind of cool. I'm going to compute the determinant of a 4x4 matrix using elementary matrices and row operations. Elementary matrices are matrices that can be obtained from the identity matrix using a single row operation. And it's a pretty cool way of solving for the determinant. So let's go ahead and start with that. We'll jump ahead to the slide that we can find this determinant on. Right here. So first of all, again, what is an elementary matrix? An elementary matrix, an n by n one, capital E, call it, is, like I said a second ago, a matrix that can be obtained by applying one elementary row operation to the n by n identity matrix In, with 1's all the main diagonal, 0's all below it, and 0's all above it. It turns out, this is the cool part, the corresponding row operation can be accomplished, the row operation to obtain E from In can be accomplished on an arbitrary n by n matrix, capital A, using left multiplication by capital E to get the matrix E times A. This is the cool part, that actually works. And I'm going to show you an example, but you should check it on your own. This fact, along with properties of determinants and elementary row operations that I've been talking about recently, can be combined to find the determinant of large matrices. And when I say large, I mean 4x4 or larger, in kind of a fun way with the help of technology like Mathematica we're about to show you. So let's do that. Let's use elementary matrices, properties of determinants, and Mathematica to find the determinant of this 4x4 matrix. Maybe you want to pause the video and just take the determinant of that right away. Actually, I had one student whose favorite thing to do as a math major was just take determinants of big matrices like this. I don't know why, but they had a lot of fun with it. This will be fun, though. We use the technology in a fun way. So here's the Mathematica that will help us do this. Let's just see what the answer is ahead of time. If I put this matrix inside the determinant operator in Mathematica, it will give us the answer to be -63. And whenever you see the determinant of a square matrix like this and you see that it's non-zero, right away the first thing you should think is, hey, that means this matrix is invertible. Its determinant is non-zero. All right, so what are we going to do? I'm going to call this matrix little a, and I'm going to look at little a and say, hey, what's the first elementary row operation that I'd want to do to this matrix to get it into reduced row echelon form, or even just row echelon form will be good enough to help us compute the determinant. I'd want to get a 0 underneath that leading 1 in the top row in all three of these rows, row 2, row 3, and row 4. So start by multiplying row 1 by -2 and adding it to row 2, putting the answer in row 2 to get a 0 right there, because -2 plus 2 is 0. That can be accomplished by left multiplication by this elementary matrix right here, because this is an elementary matrix. Because what I did was I took the identity matrix, the 4x4 identity matrix, with all 1's along the main diagonal, all 0's below it, and all 0's above it, and I multiplied row 1 of that by -2 and added it to row 2 to get a -2 there. This multiplication will accomplish that row operation. Let's double check it. I multiply row 1 by -2 and add it to row 2. Gives me a 0 there, like you see a 0 there. -2 times -2 is +4. +4 times -5 is -1. You see a -1 right there. -2 times 3 is -6. Plus 1 is -5. You see a -5 right there. And 1 times -2 is -2. Plus -4 is -6. You see a -6 right there. It worked. And it did not affect row 1, row 3, or row 4. Those stayed the same as they were originally. You can compare those. All right, that's the first step. Now I want to get a 0 here in row 3. Multiply row 1 by 3 and add to row 3, putting the answer in row 3. Use left multiplication by this elementary matrix, obtained from the identity matrix by multiplying row 1 by 3 and adding to row 3 and putting the answer in row 3 to get a 3 there. Lots of 3's. Multiply the previous matrix, which I call little b, by that on the left. The dot, by the way, in Mathematica does the actual multiplication. The matrix form allows me to see the answer as a nice matrix, and there we have it. We see a 0 right here as I wanted. Let's take the time to double check that quick. So this was our last matrix right here. We were multiplying row 1 by 3 adding to row 3, putting the answer in row 3. 3 times 1 is 3, plus negative 3 is 0. You see a 0 there. 3 times negative 2 is negative 6, plus 1 is negative 5. You get a negative 5 right there. 3 times 3 is 9, plus 5 is 14. You see a 14 there. 3 times 1 is 3, plus 8 is 11. You see an 11 right there. And again, rows 1, 2, and 4 stayed as they were originally. Now get a 0 down there, multiply row 1 by negative 5, and add it to row 4, and put the answer in row 4, using this elementary matrix with left multiplication to get this. You can take the time to check that. Now I'd want to get a leading one in the second row. I'd want to multiply row 2 by negative 1. Remember that row replacement operations don't change the determinant, so the determinant of all these matrices so far is the same. All the output matrices, that is, not the elementary matrices. But if I multiply a row by negative 1, I will flip the sign of its determinant. So that will change the determinant, but it is something I'm going to do. Here's an elementary matrix where I multiplied row 2 by negative 1. I'm now left multiplying that matrix times d. And that has now changed row 2 to be the opposite of the original row 2 right there. 0 stays a 0, negative 1 becomes a positive 1, negative 5 becomes a positive 5, negative 6 becomes a positive 6. Now get zeros underneath that leading one, multiply row 2 by 5 and add it to row 3, multiply row 2 by negative 8 and add it to row 4. Here's where I multiplied by 5 to get this answer, and here's where I multiplied by negative 8 to get this answer. 2 row operations done. Next step, I want a leading one in the third row. It's a 39. I need to multiply the third row by 1/39. Multiplying a row by a scalar other than 1 will change the determinant. I will get a new matrix whose determinant is 1/39, the determinant of this, and negative 1/39, the determinant of the original matrix. Don't forget that I multiplied a row by negative 1. So here's an elementary matrix where I multiply row 3 by 1/39. Gives me this. And I do get a fraction. That shouldn't be surprising. One thing left to do a row replacement operation to get a 0 there. We will not be in reduced row echelon form, but we will be in echelon form. We will have an upper triangular matrix. Multiply row, and that'll be good enough to find the determinant as the product of the numbers on the main diagonal. Multiply row 3 by 51, add to row 4, put the answer in row 4, gives you a 0 there. What does it give you there? According to Mathematica, it gives me that. Okay? So remember, row replacement operations do not change the determinant. There were plenty of row replacement operations I did. Multiplying a row by negative 1, as I did once, changes the sign of the determinant. It multiplies it by negative 1. Multiplying a row by a constant other than 1 changes the determinant. Here I multiplied by 1/39. And because I had already done a multiplication by negative 1, this matrix right here has a determinant negative 1/39, the original. This one's going to have a determinant then negative 1/39, the original. But its determinant is 21/13. Because it's upper triangular, I can find its determinant by multiplying the numbers on the main diagonal. 1 times 1 times 1 times 21/13. Its determinant is 21/13. Now multiply that by negative 39 to get the determinant of the original to be negative 63, as we saw before. Isn't that cool? Pretty fun. I multiplied by negative 39 because I got to go back to the original matrix. These new matrices had a determinant negative 1/39, the determinant of the original. So I have to multiply by negative 39 to get the determinant of the original. All right, fun, fun, fun. Let's now go on to vector spaces and linear transformations, our main topic for the lecture. I got to go fast here first. These first few slides are slides I went over in lecture 15B. I introduced vector spaces and the definition involving some axioms and properties that we assume to be true, some basic facts that followed, and I also mentioned some other more involved facts. These first few slides, because it's a review, I'm going to go quickly. A vector space, also called a linear space, is first of all a non-empty set where there are two operations that are defined with respect to elements of this non-empty set V and real numbers. These two operations are called vector addition and scalar multiplication. Okay? Keep that in mind. And when you think about these abstract properties, it's good to think about examples. Our prominent example being Rn. the vector space of all n-dimensional, say, column vectors with real number entries that you can add in the usual way and multiply by scalars in the usual way. But you need to be able to think abstractly as well. So while you keep that example in mind, you want to be able to work at a purely symbolic, definitional, theorem, logical level, okay? You want to be able to think abstractly. That is important to seeing the connections. So we have these properties with respect to addition and scalar multiplication. First of all, this set of 5 properties. First one is closure under addition. Given any two vectors in capital V, their sum is in capital V. I am using boldface notation for these abstract vectors just to emphasize that they are vectors in a vector space. But in the abstract setting, they are not necessarily column vectors. They could be functions, in fact. Some of the examples, they will be functions. The examples that are related to differential equations, they will be functions. Commutative property holds, associative property holds. There is a zero vector, an additive identity, u plus 0 equals u for all u. Again, upside down a's mean for all, backwards e's means there exists. These symbols mean 0 is an element of v. St is shorthand for such that. 5 says every element has an additive inverse, which we denote by negative u. This does allow us to define vector subtraction if we want, and we do want, though it's not on these slides. We define u minus v to be u plus the additive inverse of v. That's the definition of vector subtraction. And notice it would mean vector subtraction is not commutative. V minus u would be v plus the additive inverse of u, and these are not the same in general. Not the same. Not equal in general. Okay? So yes, we could define vector subtraction, and I will sometimes think in terms of vector subtraction, but vector subtraction is defined in terms of vector addition. It's not an axiom. And then we have these other 5 properties. Excuse me. Closure under scalar multiplication. Alpha is a scalar, which means a real number. And by the way, that's where the real vector space label comes from, because the scalars are real numbers. There's actually nothing stopping us from allowing scalars to be complex numbers or numbers from any other number field. I won't go into more details. This is going to be good enough for us. There's two distributive properties, 7 and 8. There's an associative property with scalars times vectors and scalars times scalars. And the number 1, acts as a scalar multiplicative identity. Okay? These are worth trying to remember, even though for my students you don't have to technically memorize them. It's good for you to try to memorize them. That's going to be more quick to come to your mind when you need to think about them. The names do help. They are descriptive. Examples of vector spaces. This is review as well. There's our most prominent example, n-dimensional Euclidean space. R means the real numbers. These can be thought of in one of 2 ways, either as n tuples column vectors, n by 1 matrices that have real number entries, or you could think of them as row vectors if you wanted to, or points that you can add in the usual way if you sort of associate the point with a row vector. Any one of those ways is fine. Why is it called Euclidean space? Essentially because the geometry of this is Euclidean as opposed to non-Euclidean. Things work geometrically the way you think they should. Non-Euclidean geometry is a pretty strange subject. Any zero vector, just by itself, as a singleton set with one element, is a vector space, called the trivial vector space. I am thinking of this as being a Euclidean space. I'm thinking of this as being a column vector, say, of all number zeros. Any line through the origin, when associated with the corresponding position vectors, in Euclidean space. It's a subspace of Euclidean space. I did introduce subspace last time. I'll continue this time. Any plane through the origin, again, the corresponding position vectors. Here's something new, and I added an extra notation here. The set of all polynomials, I did talk about this last time, but this is a new notation here. The set of all polynomials Pn of degree less than or equal to some positive integer n, that's fixed, that does include the zero polynomial in it, whose degree is technically undefined. Now, polynomials are functions. You can graph them, you can find their derivatives, etc. And we will sometimes think of them that way. But we also can think of them as purely algebraic objects, where essentially the powers of t, if you want to call the variable t, are just placeholders. So if we want to add two polynomials, say 5 plus 4t plus 6t squared, add that to the polynomial, say negative 2 plus 5t minus t squared. You do it like terms, right? 5 plus negative 2 is 3, 4t plus 5t is 9t, 6t minus t squared is 5t squared. This polynomial plus this one is this one. It's a closure kind of thing that just happened there. These both have degree less than or equal to 2, and this one also has degree less than or equal to 2. If I had chosen the second one appropriately, I could have made everything cancel out and gotten the zero polynomial. So again, you can think of these as functions of t, and you can graph them if you want. That's sometimes handy. But you can think of this as purely algebraic. You don't have to think about graphing them. And that's actually helpful sometimes, as we will see. The set of all functions of the form a cos t plus b sine t. And once again, you can think of this as functions that you can graph and find derivatives of and be solutions of differential equations. Or you can think of it as a purely algebraic object. You can add functions like this and you'll get another function like this, because you add like terms. You can multiply them by scalars and you get another function of this form. And addition of functions like this is commutative, associative, etc. It does satisfy all the properties. We're not going to take the time to do that, but maybe if a property is not clear to you, maybe you want to try to verify it. The zero vector, as a zero function, is an element like this because you can take a and b to both be zero to get the zero function as the zero vector for this vector space. The set of all sequences, in other words, discrete functions. Here I'm thinking of t as a real variable. Here I'm thinking of n as a discrete variable. It could be just positive integers. It could be all integers. N could be -1, -2, -3, etc. The a, b, and c, in a sense, determine the algebraic nature of these functions. I could, again, take them all to be zero, and I get the zero function, although the domain would just be the integers again. The set of all n by n matrices with real number entries, where you add matrices by entry, that's analogous to adding vectors component by component, and when you multiply them by scalars, you're multiplying those entry by entry. In all these cases, it is assumed that addition and scalar multiplication are done in the natural way. We're not doing anything weird here, though you might try doing weird things sometimes in these kind of settings. We want to do things in the natural way here. The following properties of a vector space V are true and can be proved fairly easily with a bit of ingenuity. I'm not going to take the time to do that for time's sake, but these are things you would want to be true, okay? We don't take them to be axioms. We don't take them to be part of the definition because you want to try to keep your axioms as minimal as possible. If you can prove something from an axiom or two, then you should prove it, in this case as a theorem. These are, again, these are things you would want to be true. The number 0 times any vector is the zero vector. Any number times the zero vector is also the zero vector. The number -1 times any vector is its additive inverse. If 0 prime plus u equals u for some u, then 0 prime must in fact be the zero vector. The zero vector is unique. You wouldn't want two zero vectors. If u plus u prime equals 0, then u prime must be the additive identity of u. Additive inverses of any given vector is unique. If alpha times u is 0, but alpha is not the number 0, then u must be the zero vector. If alpha times u is the zero vector, but u is not the zero vector, then in fact alpha must be the number 0. This annihilated idea in this description is just saying these things are getting mapped to 0. For example, 0 times u is the zero vector. The number 0 annihilates any vector. It maps it to 0, so to speak, under the scalar multiplication. And 0 is actually not nothing. It is something. It's just something that represents absence of something, if that made sense. All right, more fundamental definitions and more facts. Gotta go quick. This is, again, all a review. Let V be a vector space, and let H be a non-empty subset of V. So initially here, it's just a subset, okay? All the elements of H are also elements of V. If, in addition, H is also a vector space under the same operations of vector addition and scalar multiplication as in V, then we call H a subspace. Emphasis on the word space instead of subset of V. Note, both 0 by itself, this is a zero vector. This is supposed to be boldface. Zero vector, that singleton set, and V itself are both subspaces of V. They're sometimes called the trivial subspaces, two extremes, just the one element set, the zero vector, and the entire space itself. Theorem, subspace test. We will look at examples of subspaces here. A subset H is of a vector space. V will be a subspace of V if, write it as three conditions here. First of all, H is non-empty. We don't want the empty set to be a subspace for some technical reasons. If it's closed under addition, and if it's closed under scalar multiplication. All the other properties, commutativity, associativity, etc., distributive property, follow pretty easily if these things hold. The only thing that's not necessarily absolutely clear is that, for example, the zero vector is in this and additive inverses are in this. Let's look at the zero vector. I'll let you think about additive inverses. Why is the zero vector guaranteed to be in H when these conditions are whole? It's because of the closure under scalar multiplication, and it's because I can take the alpha to be the number 0, as well as a property from the previous slide. If I take alpha to be the number 0, and u to be any vector in H, then alpha u must be in H as well by closure under scalar multiplication. But alpha times u will be the zero vector by the property that when you multiply it by 0, it annihilates any non-zero vector. This is the zero vector, so therefore 0 is in H. That's a quick proof that this subspace test would imply the zero vector is in H. And again, you should take the time to verify additive inverses. And you can use property 3 again with another value of alpha. Here's a very important definition, the definition of the span of a set of vectors. Let V1 through Vn be elements, vectors in a vector space. The span of these vectors is the set of all linear combinations of these vectors, where a linear combination of those vectors is a sum with arbitrary scalars in front of them, arbitrary weights. Notationally, we can write this: the span of V1 through Vn is the set of everything that looks like this, where the CI's range over all real numbers. So as long as these V's are not all the zero vectors, this is going to be an infinite set because there's infinitely many C's you can choose from. Don't ever think this is a finite set, even though there's a finite list of vectors here. The span of that is an infinite set. Theorem. The span of any finite collection of vectors in an arbitrary vector space is a subspace of that vector space. I'm not going to fully prove this with an argument here, writing sentences, but let me give you the idea. You'd have to use the subspace test. First, is the set non-empty? Sure, because the C's can be anything. Even if all the V's were the zero vector, it would still be non-empty because I'd still could pick C to be anything and I'd get the zero vector. The C is allowed to be anything says this is going to be non-empty. That's trivial. Is it closed under vector addition? Take an arbitrary combination like this and add it to another arbitrary combination like this. The question is the sum a similar kind of arbitrary combination? If it is, then it's going to be closed under vector addition. And after some work with axioms of the vector space, like associativity, like commutativity, like the distributive property, ... is the work in between, you would be able to show that this sum can be written this way. And that means it's in the right form. It is in the span because I've got these coefficients. I've got a linear combination of V1 through Vn. That would imply it's closed under vector addition. Is it closed under scalar multiplication? I could take an arbitrary vector in the span and multiply it by an arbitrary scalar. And once again, distributive property along with associativity is going to imply, you can write this kind of thing. Sorry, this is not so dark anymore. Cn times Vn, and that's going to be of the right form to say it's closed under scalar multiplication because there we have another linear combination of V1 through Vn. Okay, so now you need to fill in the details if your teacher asked you to prove this theorem. Linear transformations are essential. In fact, you might even say the study of vector spaces is more about the linear transformations than it is about the vector spaces themselves, though the linear transformations help you understand the vector spaces and vice versa. Let V and W be vector spaces, and suppose T is a function whose domain is V and whose codomain is W. We call T a linear transformation, or linear map, or linear mapping. All three words are used, though I didn't put the mapping one, from V to W if it is operation preserving. If this equation is true for all real numbers alpha and beta and for all vectors u and v in capital V. This is our operation preserving property that we have thought about a lot in the special vector space Rn. And going back way to lecture 4, we thought about geometric linear transformations like rotations and reflections and dilations and shears and projections that satisfy this kind of property. But now we want to think about this property in the abstract. U and V could be functions. We could be talking about a function space here, and in fact we'll look at an example where they are. Alpha and beta do have to be real numbers, though. This property needs to hold for a linear transformation. It's important to note that it follows from this that T of the zero vector is 0. Why? The idea of the argument there, hopefully with a better marker. This one might be better. Well, for example, I could write T of the zero vector is T of the zero vector plus the zero vector. Why? Because the zero vector does equal 0 plus 0. And then by the operation preserving property, I can write this is T of 0 plus T of 0. Now I didn't write down a cancellation property of vector spaces with respect to addition, but there is one. I could have written it down. Essentially, you can cancel the T of the zeros from both sides and say T of 0 must be 0. What I'd really have to do to prove that is add the additive inverse of T of 0 to both sides and use properties like the commutative property, etc., associative property. But you can ultimately justify canceling because of that, and we can jump from here to here. Okay? That's something worth remembering. And that's part of the reason why we want the operation preserving property to hold. We've talked about one-to-one and onto functions before, injective and surjective. T is one-to-one, also called injective, if when you've got two distinct inputs, they get mapped to two distinct outputs. Said another way, and this way is sometimes easier to use, if you know T of u, hey, that's the better one. If you know T of u equals T of v, and you know T is one-to-one, that implies that u equals v. Or if you want to prove that T is one-to-one, you'd start with this assumption and show that this follows. Got that? This implication is equivalent to that implication. They're what's called contrapositives of each other if you want to look that up. But both mean that T is one-to-one. Another way to think about this is that T is one-to-one if each equation of this form, T of x equals b, has at most one solution for x. If I imagine b to be a fixed vector in W, and I'm wondering what vectors x in V get mapped to b, if T is one-to-one, you know there's at most one solution for x. There might not be any. There could be 0 solutions, but no more than one. So that's pretty clear. We say that T is onto, also called surjective, if for each element of W, there's something in V that gets mapped to it under T. For all vectors boldface W and capital W, there exists a boldface V and capital V such that T of E equals W. That is equivalent to saying that this equation has at least one solution for x, no matter what B is. Okay, for every B in W, there's at least one x in V. There could be more than one that gets mapped to that B. Of course, if it was a one-to-one, it would also have to be exactly one solution. Yeah, if T is one-to-one and onto, it's called bijective, and this kind of equation would have exactly one solution. What's the kernel of T? It's the set of all vectors in capital V that get mapped to the 0 vector in W, this vector right here. This 0 vector would be an element of W, the 0 vector in W, but the kernel itself is a subset of V. Many people draw these kinds of pictures, blob pictures, say V is there and W is there, and T maps from V to W, the kernel is some subset of V. Those are all the elements that get mapped to the 0 vector, which is one element in W. The image of a subset S of V under T is defined by this equation. It's the set of all outputs T of V as boldface V varies over the subset S of V. Again, the picture would be helpful if you draw V here and W there. S would be some subset of V. What are all the points those points get mapped to in W? This is a subset of W. It's very important to think about these things very carefully to make sure you understand them. We can also talk about the overall image of T. In T is the image of V under T. It's a subset of W. We can say a little bit more about these things, but before we talk about those more, I want to show you some examples of linear transformations. We're getting close to the end here. Hang with me here. Pretty important to think about examples too. There's our standard example. If A is an n by n matrix, then T from Rn to Rm defined by matrix multiplication, T of x equals A times x, is a linear transformation. Okay, we've talked about that kind of example a lot. Just now we're putting this in the context of the abstract vector spaces and the abstract linear transformations. Is such a T one-to-one and onto? We thought about that before with examples. The answer is it depends. Okay? Though I will say once again, without writing it down, that if T maps a higher dimensional space to a lower dimensional space, big space to small space, it can't possibly be one-to-one, at least when the transformation is linear. Maybe there could be nonlinear transformations that could still be one-to-one. And it's most likely going to be onto, though it's not a guarantee. On the other hand, if you map a low dimensional space to a high dimensional space, it's guaranteed to not be onto, but most likely it'll be one-to-one, though it doesn't have to be one-to-one. If the dimension of the domain and the codomain are the same, if they're both Rn, say, then most likely T is both one-to-one and onto. If you pick the entries of the matrix A at random, in all likelihood, with probability 1, it will be one-to-one and onto for that square matrix when n and m are equal. Though you can certainly come up with examples where it's not invertible, where T is not one-to-one and not onto. And actually, in that case, if it's not one-to-one, it's also not onto, and vice versa. Function space example. Let C square bracket A comma B be the vector space of all real-valued continuous functions on the closed interval from A to B. I picked a closed interval. I could have picked an open interval. I could have picked the entire real number line, in fact. So don't let that bother you. And let C1 square bracket A comma B be another vector space. It is a different vector space. All real-valued functions that are continuously differentiable on the closed interval from A to B. And actually, if I used an open interval here, it would be a little easier to define exactly what this means, because by having a closed interval, I have to talk about differentiability at the endpoints, which really means you need to think about one-sided derivatives. Continuously differentiable, I have talked about in the differential equations part of this course, in the context of phase lines and the linearization theorem. Continuously differentiable functions are those functions that are differentiable, they have a derivative, but also that derivative is continuous everywhere. The continuity and the continuously differentiable parts here are on the entire closed interval. All right, the function t from C1AB to CAB, this is the domain, this is the codomain, defined by the formula t of f equals f prime is a linear transformation. What does this mean? T is mapping any continuously differentiable function, f, defined on the closed interval from A to B, real value to real outputs, to its derivative, which is going to be continuous, because I'm assuming f is continuously differentiable. I'm not saying what the independent variable for the function is. I could give it a name. I could call it little t or little x or something, the most common things to use. But what I'm thinking about when I think about this is I'm thinking about the functions themselves as being elements of the vector space. They are the vectors. And t is a function of functions. We could call it a linear operator even, like we've been talking about in the lecture A's with linear differential equations. I could have used a y instead of an f. I could say t of y equals y prime, where y is a function of, say, little t, just like with differential equations. By using just an f prime, I don't need to worry about what the independent variable is for the little f here. This capital T takes a function as input that's continuously differentiable in here and maps it to a continuous function, its derivative. It's guaranteed to be continuous because I'm assuming the input is continuously differentiable, and I see a small typo here. This should be a comma. Okay. Is this one-to-one? Is it onto? Is it linear? It is linear. Why? Because differentiation is linear. You know that from Calculus 1. T of, say, alpha f plus beta g is the derivative of alpha f plus beta g, where alpha and beta are real numbers. They're the scalars. F and g are functions, continuously differentiable functions. That's alpha times f prime plus beta times g prime. And again, I'm not bothering to put the of, say, little t's in here. I could. I'm not bothering to emphasize the elements are functions. The function in all its glory, so to speak, is one vector. It's one element of the function space. That's hard to get used to. I'm thinking of them holistically. Here's another example that's related. Let Pn be the vector space of all polynomials of degree less than or equal to n. Define a linear transformation from Pn to Pn minus 1. Oh, I guess I forgot to answer these questions. Okay, let's do that quick. Is T 1-to-1? You think about it. No, it's not. Why? Because T of f plus any constant, c, constant function, is f plus c prime is f prime plus the zero function is f prime, which is T of f. And if c is non-zero, we've got two different inputs getting mapped to the same output, f prime. So no, T is not 1-to-1. Is it onto? That's harder to prove. It is onto, though. And it's essentially because any continuous function has an antiderivative. It's integral, essentially. Let me go ahead and write it. It's worth writing. Got a little f, little f function, and I'm trying to define a capital F function that's going to be an antiderivative of it. Okay, I need the variable here. Use an integral to define it. Use, say, a dummy variable like u over here. This will have the property that T of capital F equals little f. And if little f is continuous, that's going to be true. That's it's sometimes called the first fundamental theorem of calculus, and some books call it the second fundamental theorem of calculus. This is a similar example again. Pn is the vector space of all polynomials of degree less than or equal to n. Define T from Pn to Pn minus 1, degree less than or equal to n, degree less than or equal to n minus 1, by this formula. T of this polynomial is this polynomial. Doesn't that look interesting? That looks like I just differentiated this polynomial to get this polynomial. Yeah, these are really the same linear transformation, although the domains are different and the codomains are different. I am differentiating here, though now I'm thinking of it as more algebraic in terms of the power rule back from Calc 1 as well. The derivative of x to the n is n times x to the n minus 1, and assuming the linearity with the coefficients holds, I did essentially take the derivative there. And that also is not 1-to-1, but is onto. What do you think about that? You don't need the fundamental theorem of calculus to verify it's onto, though. You can do it purely algebraically. All right, I think this is our last slide. More fundamental definitions and facts. These are very factually oriented terminology, theorems. You gotta work at it. okay? You can't just ignore this if you're going to do well in the course. Let T be a linear transformation from V to W. A linear transformation between vector spaces. I added between vector spaces. I didn't have to. It's really assumed it would be if I say it's a linear transformation. Then, the kernel of T is a subspace of V, and the image of T is a subspace of W. In fact, the image T of H of any subspace H of V is a subspace of W. Picture might be helpful here. Some people might argue I shouldn't draw my vector spaces as blobs because vector spaces are rigid. Okay, don't worry about it. Here's the zero vector over here. The kernel is some set over here. That's the set of all the vectors in capital V that get mapped to the zero vector. And if it contains more than just the zero vector, this function won't be one-to-one. If H is an arbitrary subspace of V, maybe bigger than the kernel. Does it contain the kernel? Maybe, maybe not. If that's H, T of H is the set of everything that those vectors get mapped to. That's, if H is a subspace of V, then T of H is going to be a subspace of W. How do you prove this? Use the subspace test. Verify that these things are non-empty, verify that they're closed under addition, and verify that they're closed under scalar multiplication. I'll probably give that as an exercise to my class. Corollary. Let A be an n by n matrix, then the null space is a subspace of Rn, and the column space is a subspace of Rm. What's the null space of A? It's the set of all vectors such that A times x is the zero vector. That's the definition of the column space. That sounds a lot like the definition of the kernel of a linear transformation. Yeah, it is, if the linear transformation is from Rn to Rm. It's a subspace because the kernel is a subspace, the kernel of the associated T. The column space is the set of all linear combinations of the columns of A, and I did talk about recently how that's the same as the image of T. And therefore, this is a corollary of the theorem. Column space of a matrix and its null space are subspaces of the appropriate vector space. Another theorem. Let V from V to W be a linear transformation. Then T is one-to-one if and only if the kernel is just the zero vector. Remember, T of 0 is always 0 for linear transformations, so the kernel certainly contains the zero vector. If you know T is one-to-one, then certainly the zero vector is the only thing that gets mapped to 0. So certainly this direction, assuming it's one-to-one, implying the kernel is just the zero vector is pretty easy. A little trickier the other way. If you assume the kernel is just the zero vector, then T must be one-to-one. I'll let you think about that. Maybe I'll assign it to my students as an exercise. It involves using the operation preserving property of linear transformations. To verify this, you could assume T of U equals T of V and show that U must equal V if you assume the kernel is just the zero vector. It's not too hard, but it takes a little bit of ingenuity. It's really a definition that T is onto if and only if the image of T is all of W. That's a definition. This is a theorem. You need to prove this. This is a definition, which I mentioned before in the less abstract case. Any function is onto if its image is the entire codomain. Everything in the codomain is an element of the image. There's something in the domain that gets mapped to it. You don't need to prove that. That's a definition. A couple notes to end here related to inverse functions, which we'll talk about to come here. We know that a function will be invertible if and only if it is both one-to-one and onto. It's bijective. And that'll mean a linear transformation is invertible if its kernel is just the zero vector and if its image is the entire codomain. It's worth remarking, though we won't make use of it really, that the onto assumption about functions leading to invertibility can be gotten around if it's not onto. If T is not onto, we can make it be onto How? By appropriately restricting or shrinking the codomain. So if this T here was not onto all of W, we could shrink the codomain to some subspace of W where T would be onto that codomain, and you could then technically, as long as T is 1-to-1, define an inverse function. The 1-to-1 is absolutely necessary to have inverse functions. Yes, and this is the last slide. Thanks for watching.